All right, let's jump right into this explainer. Today we're not just looking at a bunch of dry, abstract equations on a whiteboard. No, we're going to view the microscopic world of particle physics as what it really is, a totally high-stakes, meticulously governed game of cosmic billiards. Imagine an impossibly tiny pool table where the balls are fundamental particles, and the break dictates the very structure of matter itself. This isn't just theory, guys. These are the exact mechanics powering the burning of stars and the hum of nuclear reactors.
Picture the dense nucleus of an atom sitting right at the center of the table. That's our target, basically the rack of balls waiting to be hit. Our focus today is squarely on that center. We're going to explore exactly what happens when we break that rack by bombarding the target nucleus with a beam of monoenergetic projectile particles. So here's our roadmap. First up, the cosmic billiard break. Then we'll bounce through the three big outcomes: elastic scattering, inelastic scattering, and true nuclear reactions. Finally, we'll wrap it all up with the unbreakable conservation laws that hold it all together. Let's do this.
Part 1. The cosmic billiard break. This is that initial chaotic moment of impact between our projectile and the target nucleus.
Okay, let's dive into this. When that incoming particle actually smacks into the target nucleus, it's not just random chaos. The laws of physics step in, and they essentially allow for three possible moves or outcomes to happen from this bombardment. You've got elastic scattering, inelastic scattering, and true nuclear reactions. And sometimes they even happen jointly. Let's break them down one by one.
Moving to our first possible move, Section 2, elastic scattering. Think of this as the perfect rebound.
If we look at the basic notation here, that little lowercase a is our incoming incident particle, and the big capital X is our target nucleus. They smash together, and what comes out? Well, exactly what went in, X and A. They simply scatter away due to their mutual interaction. The absolute defining rule here is that their total kinetic energy doesn't change one bit. It is 100% conserved. It's literally the ultimate cosmic bounce pass.
To put that into a concrete perspective, imagine a single neutron rocketing toward a massive uranium-238 nucleus. Boom. But because this is an elastic collision, the result is simply that same neutron and that same uranium-238 nucleus bouncing away from each other. The players on the board haven't changed at all, and their total kinetic energy is perfectly intact.
All right, let's transition to the second type of interaction. Section 3, inelastic scattering. This is where the rules about energy completely flip.
Now, unlike that perfect energy conservation we just saw, in an inelastic event, kinetic energy is absolutely not conserved. But remember the golden rule of physics. Energy can't just disappear into nowhere, right? Instead, the outgoing particle actually flies off with less energy than it came in with. Why? Because a chunk of that kinetic energy was swallowed directly by the target nucleus itself. So, what happens to a nucleus when it suddenly absorbs all that extra energy? Well, it gets excited. Mathematically, we show this excited state with a little asterisk, but it can't hold on to that buzz forever. Take elements like nitrogen-14 or lead-208. First, they absorb the hit and get all riled up. Then, to shed that excess baggage and chill back down to a stable ground state, they fire off a gamma ray. The internal structure hasn't changed, but it had to vent some radiation to stabilize.
Which brings us to Section 4, true nuclear reactions. This is the third potential outcome, and it's where the actual internal structure of the target is permanently altered.
This right here is where the magic really happens. Our energetic little incident particle A hits target X. But they don't just bounce, and they don't just vent energy. The collision fundamentally transforms them. We are left with a brand new residual nucleus, Y, and a completely different outgoing particle, B. The very identities of the players have been totally rewritten.
Now, what's really interesting about this slide is seeing this real-world alchemy in action. Consider an incoming neutron bombarding a target nucleus of lead-208. The impact literally shatters and rearranges the internal guts of the lead, transmuting it into an entirely different element, thallium-208. And during that violent process, the incident neutron is swapped out, violently kicking out a proton as the new outgoing particle.
Obviously, writing out those full elemental equations all the time gets super cumbersome, so physicists use this brilliant compact notation. It's basically an elegant mathematical shorthand.
You bracket the projectile and outgoing particles, A and B, right in the middle, and you flank them with the original target, X, on the left and the newly forged nucleus, Y, on the right. So that transmutation of lead into thallium we just talked about, it's quickly communicated as lead-208 and NP exchange yielding thallium-208. Super clean, simple, and efficient. And finally, we reach the climax of our explainer, Section 5, the unbreakable conservation laws, the universe's ultimate accounting system.
Because listen, no matter how violent or mathematically transformative these subatomic collisions are, the universe keeps perfect score. There are specific entities that act as constants of motion. They are strictly conserved across all nuclear reactions. These four fundamental accounting pillars are total electric charge, which is Z, total mass number, or the nucleon count, A, linear momentum, and finally, angular momentum. Let's see just how strict this accounting really is.
And this brilliantly illustrates the rigid math behind the cosmic chaos. The universe balances its books flawlessly. The total atomic charge of the particles going into the crash will exactly equal the charge of the particles coming out. Same applies to the mass number. Every single nucleon is accounted for. And linear momentum follows suit. The total momentum before the impact perfectly matches the momentum of the reaction products flying away.
Let's actually put this universal accounting to the test. Let's look at a helium alpha particle reacting with boron-10 to form carbon-13 and a proton. Check the charge. 2 protons from helium plus 5 from boron gives us 7 initially. After the crash, 6 from carbon plus 1 from the proton, exactly 7. The mass number follows the exact same unbreakable rule. 4 plus 10 is 14, perfectly matching the final 13 plus 1. Honestly, it's incredible. The ledger never has a missing cent.
And it goes even deeper. The universe's accounting even extends to invisible rotations. This equation proves the conservation of angular momentum. It shows that both the internal nuclear spin, represented by I, and the relative orbital angular momentum, the L, are seamlessly conserved. From the initial state of the target and projectile, right through to the final state of the residual nucleus and the outgoing particle, it's all balanced. It is an absolute constant of motion.
So we've seen how this high-stakes game of cosmic billiards plays out. We've watched solid elements transmute and energy totally shift forms. Yet through all of that, not a single drop of charge, mass, or momentum is ever lost or misplaced. So I want to leave you with this to think about. If the microscopic chaos of atomic collisions is governed by such flawless, unbreakable mathematical conservation, what other hidden rules is the universe playing by that we haven't even noticed yet? Thanks for hanging out with me for this explainer, and keep questioning the mechanics of the incredible world around you.